Hello, in this lecture we find out the area of the green semicircle using two different methods. In the drawing we have two semicircles. This is the white semicircle, this is the green semicircle. In addition, we know that this is line segment AC, is equals to 5 units in its length. This is line segment CV, is equals to 1 unit in its length. Again, our mission is to find out the area of this green semicircle. So in the first step, we join points P and B together by a straight line. So in the next step, I'll copy the white semicircle and we'll implement all 7 on the white semicircle. So actually, this is the white semicircle that goes from the original drawing. AB is the diameter of this white semicircle, so I'll write it down. AB is the diameter of the white semicircle. This white semicircle. By joining points P and B together by a straight line, we get the peripheral angle APB. This is peripheral angle APB that is subtended on AB, that is the diameter of this circle. Again, we have peripheral angle APB, this is subtended on AB, that is the diameter of this semicircle. Therefore, we can implement here rule 7. I'll repeat quickly on rule 7. According to rule 7, if a peripheral angle is subtended on the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing we have a circle, and this is line segment AB, that is the diameter of this circle, and we have peripheral angle ACB. This is peripheral angle ACB, this is subtended on AB, that is the diameter of this circle, and therefore according to this rule, rule 7, peripheral angle ACB equals to 90 degrees in its size. So whenever you have a peripheral angle that is subtended on the diameter of the circle, according to this rule, rule 7, it must be equal to 90 degrees in its size. So I can actually implement rule 7 in our drawing. Why? Because in our drawing we have peripheral angle APB. This is peripheral angle APB that is subtended on AB, that is the diameter of this white semicircle, and therefore according to rule 7, peripheral angle APB must be equal to 90 degrees in its size. Okay. In the next step, we join points P and C together by a straight line. and I copy the green semicircle and we implement all 7 on the green semicircle. So actually, this is the green semicircle that I copy from the original drawing. Actually, by joining points P and C together by straight line, we created a peripheral ACP. This is peripheral ACP, and we know that AP is the diameter of the green semicircle. So I write it down. AP is the diameter of this green semicircle. And we have here peripheral ACP that is subtended on AP, that is the diameter of this green semicircle, and according to rule 7, any peripheral that is subtended on the diameter of the circle must be equal to 90 degrees in inside. Therefore, this peripheral ACP must be equal to 90 degrees. So, if we focus on the original drawing, this angle A is a common angle that belongs both to the green triangle APC, and this angle A also belongs to triangle APB. Therefore, angle A is a common angle that belongs to both triangles. So we define the size of this common angle A as alpha. So here, according to our definition, this common angle A equals to alpha. So in this right triangle APB, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equals to 180 degrees. That is the sum of the angles in any triangle. Likewise, we define we define this common angle A as alpha. Or this angle A equals to alpha according to our definition. So in the right triangle ACP, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. So in the next step, I copied this right triangle APC in this right triangle APB in a new page, and we prove that those two right triangles are similar to each other according to angle similarity rule. So here, this is the right triangle APC, and this is the right triangle APB is the curve from the original drawing. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So actually this is angle APB. And this is equals to this angle, this is actually angle ACP in the green triangle. So actually proving that this is the right triangle APB that is similar to this green triangle, triangle APC. So we found out actually that angle APB in the right triangle equals to angle ACP in the green triangle. They are both equal to 90 degrees. They are both equal to 90 degrees, therefore they are equal to each other. Again, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha. This is a common angle that belongs to both triangles, so we can write down that angle alpha equals to itself as a common angle that belongs to both triangles. So if we relate to this angle alpha as it belongs to this right triangle, it will be defined as angle PAB. And angle alpha equals to itself. So if we relate to angle alpha as it belongs to this green triangle, it will be defined the circle PAC. Repeat again. This equation means that angle alpha equals to itself. We just call to angle alpha two different names. Angle alpha equals to itself is a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually this is angle ABP in the right triangle, APB. And it is equals to this angle, it is actually angle APC in the green triangle APC. Repeat again, I actually found out that angle ABP in the right triangle equals to angle APC in the green triangle. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So I actually found out that all the triangles in this green triangle APC are correspondingly equal to all the triangles in this right triangle APB. Therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. Found out that the green triangle APC is similar, this is the sign of similar, to the white triangle APB according to angle similarity rule. And for the fact that the two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AB in the right triangle over side AP in the green triangle equals to side AP in the white triangle over side AC in the green triangle. Repeat again, we derive that AB over AP equals to AP over AC. What is the length of AB? From the original drawing, it is very easy to see that AB in total equals to 5 plus 1, that is 6. Again, AB equals to 6. AB equals to 6 units in its length. And it is given as the question that AC equals to 5. AC equals to 5. So actually found out that AB over AP equals to AP over AC. AB is 6 over AP. AP is the missing side, so we do it as it is, and it is equals to AP over AC. AC is 5. So if we found out that 6 over AP equals to AP over 6. Here we cross multiply this equation, and we get that 5 times 6 is 30. So 30 equals to AP times AP, that is AP squared. 30 equals to AP squared. Here we take a root out of this equation, and you get that the missing side AP equals to the square root of 30 units in its length. The missing side AP equals to the square root of 30 units in its length. This is the missing side AP, that is equals to the square root of 30 units in its length. But what is AP? We already found out that AP is the diameter of this green semicircle. If AP is the diameter, it means that AP over 2 is the radius of this green semicircle. So we define the radius of this green semicircle as R. So R, the radius of the green semicircle, equals to the diameter AP over 2. AP is square root of 30, and therefore the radius R equals to the square root of 30 over 2. The radius R of this green semicircle equals to the square root of 30 over 2 units in its length. Our mission is to find out the area of this green semicircle. And the area of this green semicircle equals to pi r squared over 2. So write it down. The area that we are looking for in this question is the area of the green semicircle, and the area of the green semicircle is equals to pi r squared over 2. So the area of the green semicircle equals to pi. R is square root of 30 over 2, therefore r squared is square root of 30 over 2 squared divided by 2. We'll open the brackets of this expression and we get that the area of the green semicircle in total equals to pi, and square root of 30 squared is 30, over 2 squared is 4, divided by 2. So in total, the area of the green semicircle equals to pi, and 30 over 4 over 2 is 30 over 4 times 2. So in total, the area of the green semicircle equals to 30 pi over 4 times 2. 30 over 2 is 15, so in total, this expression equals to 15 pi over 4. 15 over 4 is 3.75, so in total, this expression equals to 3.75 pi. Or in terms of numbers, it is 11.78. In conclusion, we actually found out that the area that we are looking for, that is the area of the green semicircle, it is equals to either 3.75 pi square units, or in terms of numbers, it is equals to 11.78 square units. Repeat again, according to the first method, we actually found out that the area of this green semicircle equals to either 3.75 pi square units, or in terms of numbers, it is equals to 11.78 square units. We finished with the first method. In the next step, I will present to you how to find out the area of this green semicircle according to the second method. In the second method, we join points In the second method, we join points P and B together by straight line. and I'll copy the white semicircle, and we'll implement again rule 7 on the white semicircle as we did in the first method. Exactly as we did in the first method. So actually, this is the white semicircle that I copied from the original drawing. We know that AB is the diameter of this white semicircle, so we write it down. AB is the diameter of the white semicircle. By joining points P and B together by a straight line, we get the peripheral angle APB. Again, this is peripheral angle APB, and it is subtended on AB, that is the diameter of this white semicircle, and therefore according to rule 7, peripheral angle APB must be equal to 90 degrees in its size. Okay. From drawing, it is very easy to see that line segment BP is perpendicular to PA. Again, line segment BP is perpendicular to PA because of the fact that this again equals to 90 degrees. But what is PA? Know that PA is the diameter of this green semicircle. So we define the center of this green semicircle, this point O. So point O is the center of this green semicircle, point P is the point of the green semicircle itself, therefore OP is the radius of this semicircle. We'll define the radius of this green semicircle as R, therefore OP equals to R. Okay, so in the next step, I'll copy the green semicircle with line segment BP and BA in a new page, and we write this green semicircle. We already found out that this angle APB equals to 90 degrees in its size, according to rule 7. this is the green semicircle that I copied from the original drawing. We have already found out that line 7BP is perpendicular to PA. In the next step, I'll copy point O from this original drawing to the new drawing. So this is point O, this is the point from the original drawing, and we already found out that OP is the radius of this green semicircle that is equals to R. And therefore actually we found out that line segment BP is perpendicular to the radius PO. Again, line segment BP is perpendicular to the radius PO because of the fact that we have already found out that angle APB is the right angle. We found out that according to Rule 7, angle APB, peripheral angle APB is the right angle. It means that line segment BP is perpendicular to the radius PO of this green semicircle. And therefore, we can implement here Rule 1. And please quickly on Rule 1. According to Rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle and we have OM is the radius of this circle that is equals to R. And we have here line segment AB is perpendicular to the radius MO. Again, line segment AB is perpendicular to the radius MO. And whenever you have a line segment that is perpendicular to the radius, then this line segment AB is defined as a tangent. Again, whenever you have a line segment that is perpendicular to the radius, then the line segment will be defined as a tangent. So we can actually implement Rule 1 in our drawing. Why? Because in our drawing we have line segment BP that is perpendicular to the radius PO. And therefore, according to Rule 1, line segment BP must be defined as a tangent to this green circle. So write it down. According to Rule 1, this line segment BP that is perpendicular to the radius PO must be defined as a tangent to this green semicircle. And you can see that indeed line segment BP is tangent to this green semicircle at point P. Point P is the point of tendency of tangent BP with this green semicircle. Okay. So from the common point point B, we have tangent BP that is tangent to this green semicircle at point P. In addition, from the same common point B, we have here this straight line that cuts this green semicircle at 2 points A and C. In this way, we created a chord AC. Therefore, we can definitely implement here Rule 10. I'll repeat quickly on Rule 10. According to Rule 10, Rule 10 is true in any circle. So, in any circle, if AB is a chord, you can see here that AB is a chord of this circle, and PT is a tangent. Here you can see that PT is tangent to this circle at point T. So in this drawing, the following equation is true. That PT square equals to PA times PB. Again, PT square equals to PA times PB. We can definitely implement Rule 10 in our drawing. Why? Because in our drawing, if we focus on this common point B, from this common point B, first of all, we have tangent PT to this green semicircle. Tangent BP is tangent to this green semicircle at this point P. In addition, we have this straight line that creates chord AC from the same common point B. Therefore, all the requirements of Rule 10 are satisfied, and therefore we can implement in our drawing Rule 10. According to Rule 10, we get that BP square equals to BC times BA. Again, BP square equals to BC times BA. So I write it down. BP square, that is the square of the tangent. BP square, the square of tangent BP equals to BC times BA. BC times BA according to rule 10. This equation is the implementation of rule 10 in our drawing. BP square equals to BC times BA. It's given us the equation that BC equals to 1 unit in its length. And 9/7 AB in total, this is 9/7 AB, that in total equals to 5 plus 1, that is 6. Again, 9/7 BP, 9/7 AB in total equals to 5 plus 1, that is 6. Segment AB equals to 6 units in its length, and BC equals to 1. So BP square, BP is the missing tangent, so we leave it as it is. BP square equals to BC. BC is 1, therefore we substitute BC by 1 times BA. BA is 6, so we substitute BA by 6. So in total we actually found out that BP square equals to 1 times 6, that is 6. BP square equals to 6. We take a root out of this equation, and finally we get that BP equals to the square root of 6 units in its length. So the tangent BP here equals to the square root of 6 units in its length. In the next step, I'll copy the right triangle APB in a new page, and we will implement the Pythagoras theorem on this right triangle, triangle APB. The hypotenuse AB equals to 6 units in its length, and we just write down further that PB, side PB equals to the square root of 6 units in its length. The only missing side in this right triangle APB is side AP. We find out the missing side AP by implementing the Pythagoras theorem on this right triangle APB. So actually, this is the right triangle APB that according to the original drawing. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle APB is AB, therefore the square of the hypotenuse is AB squared, and it must be equal to AP squared plus PB squared. AB, the hypotenuse AB equals to 6 units in its length, therefore AB squared is 6 squared, that is 36. So 36 equals to AP squared. AP is the missing side, so we leave it as it is. Plus PB squared. PB equals to the square root of 6, therefore PB squared is square root of 6, square root of 6 squared, that is 6. So in total, we should find out that according to the Pythagoras theorem, 36 equals to AP squared plus 6. Here we subtract 6 from this equation, and we get that AP squared equals to 36 minus 6 is 30. We take a root out of this equation, and finally we get that the missing side AP equals to the square root of 30 units in its length. So this is side AP is equal to the square root of 30 units in its length. AP is the diameter of this green semicircle. If the diameter AP equals to the square root of 30 units in its length, it means that the radius must be equal to AP over 2, that is the square root of 30 over 2. So write it down. The radius of this green semicircle R equals to the diameter AP over 2. The diameter AP equals to the square root of 30, and so 30 over 2 is the radius of this green semicircle. So the radius R of this green semicircle equals to the square root of 30 over 2 square units, the square root of 30 over 2 units in its length. And our mission is to find out the area of this green semicircle. So the area of the green semicircle equals to pi r square over 2. Repeat again. The area of this green semicircle equals to pi r square over 2. So the area of the green semicircle equals to pi. R is equal to 30 over 2, therefore R is equal to 30 over 2 squared divided by 2. So it is pi, we'll open the brackets here, square root of 30 square is 30, and 2 square is 4 divided by 2. So it is pi, and 30 over 4 over 2 is 30 over 4 times 2. 30 over 2 is 15, so in total this expression equals to 15 pi over 4. 15 over 4 is 3.75, so in total this expression equals to 3.75 pi. In terms of numbers, it is equal to 11.78 square units. So actually we found out finally that the area that we are looking for, that is the area of this green semicircle, equals to either 3.75 pi square units, or in terms of numbers, it is equal to 11.78 square units. Repeat again, we should found out that the area of this green semicircle, according to the second method, it is equal to either 3.75 pi square units, or in terms of numbers, it is equal to 11.78 square units. So we finish with the second method. In the next step, I will summarize the lecture. We start with the first method, of course. In this lecture, we found out the area of this green semicircle using two different methods. So in the first method, so in the drawing, we have two semicircles. In addition, we know that this is 97AC, this is equals to 5 units in its length. This is 97CB, this is equals to 1 unit in its length. Again, our mission is to find out the area of this green semicircle. So in the first step, we join points P and B together by straight line, and then I copy the white semicircle in the new page and to implement the rule 7 on the white semicircle. This is the white semicircle that I copied from the original drawing. We know that AB is of course the diameter of this white semicircle, and by joining points P and B together by straight line, we create the triangle APB. Triangle APB is subtended on AB, the diameter of this white semicircle, and according to rule 7, any peripheral angle that is subtended on the diameter of the circle must be equal to 90 degrees in size. Therefore, peripheral angle in PB must be equal to 90 degrees in size. This angle equals 90 degrees. In the next step, we join points P and C together by straight line, and then I copied the green semicircle in a new page, and we implemented rule 7 on the green semicircle. This is actually the green semicircle that I copied from the original drawing. Again, we know that of course AP is the diameter of this green semicircle. By joining points P and C together by straight line, we can get peripheral angle ACP. Peripheral angle ACP subtended on AP, that is the diameter of this green semicircle, and according to rule 7, any peripheral angle that is subtended on the diameter of the circle must be equal to 90 degrees in its size. Therefore, this peripheral angle ACP equals to 90 degrees in its size according to rule 7. So here we have, this is angle A, that is a common angle, it belongs both to the green triangle APC, and the angle A also belongs to the white triangle, the triangle A, the right triangle APB. Therefore, angle A is a common angle that belongs to both triangles, so we define angle A as alpha. So, in this right triangle APB, angle A is defined as alpha. So in the right triangle APB, this angle equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, this right triangle APC, this angle equals to alpha because it is a common angle A that is equals to alpha. This angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. In the next step, I copied this green triangle APC and this white triangle APB in a new page, and we proved that those two right triangles are similar to each other according to angle similarity rule. So actually, those are the two right triangles that are coming from the original domain. Why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles, so we can write down that the angle alpha equals to itself is a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So I should prove that all the angles in this green right triangle APC are correspondingly equal to all the angles in this right triangle APB. Therefore, those two right triangles are similar to each other according to angle similarity rule. I repeat again, we should find out that the green triangle APC is similar to the right triangle APB according to angle similarity rule. And from the fact that the two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AB in this right triangle APB over side side AP in the green triangle equals to side AP in the white triangle over side AC in the green triangle. I repeat again, we derive that AB over AP equals to AP over AC. AB equals to 6 units in its length, AC equals to 5 units in its length. Again, AB is 6, AC is 5. Therefore, in total, this equation is equals to 6 over AP equals to AP over 5. We just multiply this equation and finally found out that 5 times 6 is 30, so 30 equals to AP times AP, that is AP squared. So 30 equals to AP squared. We took out all of this equation and finally found out that the missing side AP equals to the square root of 30 units in its length. This is the missing side AP. is equals to the square root of 30 units in itself. AP is the diameter of this green semicircle. AP is the diameter, therefore the radius is AP over 2. The radius of this green semicircle is AP over 2. Again, the radius R is the diameter AP over 2. AP is equal to 30, therefore the radius is equal to 30 over 2. In conclusion, we can find out that the radius R of this green semicircle equals to the square root of 30 over 2. Our mission is to find out the area of this green semicircle. The area of this green semicircle equals to pi r squared over 2. Repeat again, the area of the green semicircle equals to pi r squared over 2. So it is pi times r. R is equal to 30 over 2, therefore r squared is equal to 30 over 2 squared divided by 2. We open the brackets here and found out actually that in total the area of the green semicircle equals to pi, and square root of 30 square is 30, over 2 square is 4 divided by 2. So the area of the green semicircle equals to pi times 30 over 4 over 2. 30 over 4 over 2 is 30 over 4 times 2. So in total this expression equals to 30 pi over 4 times 2. 30 over 2 is 15, so in total this expression equals to 15 pi over 4. 15 over 4 is 3.75, therefore in total this expression equals to 3.75 pi. Or in terms of numbers, it is equal to 11.78. So in conclusion, we shall find out that the area of this green semicircle equals to either 3.75 pi square units, so in terms of numbers, it is equal to 11.78 square units. We finished with the first method. In the next step, I presented to you how to find out the area of this green semicircle according to the second method. In the second method, we join points P and B together by a straight line. Then I copied the white semicircle in the new page and implemented rule 7 in the white semicircle exactly as we did in the first method. So here, this is the white semicircle. By joining points P and B together by a straight line, you can identify periangle APB. We know that AB is the diameter of this semicircle, and we have here periangle APB that is subtended on the diameter of this semicircle AB, therefore it is equal to 90 degrees in its size according to rule 7. So this is periangle APB, that is a right angle according to rule 7. So here we have line 7BP that is perpendicular to PA. PA is the diameter of the green semicircle. So we define the center of this green semicircle at this point as point O. Therefore, OP is the radius of this green semicircle. So we have line 7BP is perpendicular to the radius PO. Again, line 7BP is perpendicular to the radius PO. Again, line 7BP is perpendicular to the radius PO of the green semicircle. So I copied again the green semicircle with line 7BP and line 7BA in a new page. And I also copied the center of this green semicircle that is here at point O. So here we have this is line segment BP that is perpendicular to the radius PO. And whenever you have a line segment that is perpendicular to the radius, you can implement rule 1. I'll repeat quickly of rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle and we have the radius OM that is equals to R. The radius OM is perpendicular to line segment AB, or line segment AB is perpendicular to the radius MO. And because of the fact that line segment AB is perpendicular to the radius MO, line segment AB is defined as a tangent to this circle. Again, line segment AB is a tangent to this circle because of the fact that line segment AB is perpendicular to the radius MO. So whenever you have a line segment that is perpendicular to the radius, then the line segment must be defined as a tangent. So we can implement rule 1 in our drawing. Why? Because in our drawing we have here line segment BP is perpendicular to the radius PO, and therefore according to rule 1, line segment BP must be a tangent. Line segment BP is tangent to this green semicircle according to rule 1, because it is perpendicular to the radius PO of this green semicircle. So line segment BP is perpendicular to the radius PO, and line segment BP is defined as a tangent to this green semicircle, and line segment BP is tangent to this green semicircle at point P. And in addition, we have here, from the same connection point B, we have here this red line that cuts this semicircle at 2 points C and A. So we have here a chord CA from the connection point B, and in addition we also have line segment BP that is tangent to this semicircle at point P. Therefore we can implement here rule 10. According to rule 10 is true in any circle. So in any circle, if AB is a chord, you can see here that AB is indeed a chord of this circle, and we have also PT is a tangent to this circle, PT is tangent to this circle, this point T. So in this drawing, the following equation is true, that PT square equals to PA times PB. Again, PT square equals to PA times PB. We can definitely implement rule 10 in our drawing. Why? Because in our drawing, we have here, from the connection point B, we have tangent BP, that is tangent to this green semicircle at point P. And in addition, we have from the same connection point B, this straight line that cuts the circle, the semicircle, the green semicircle to point C and A. This way created here chord AC. So all the requirements of rule 10 are satisfied, and therefore we can implement rule 10. According to rule 10, we get that BP square equals to BC times BA. Again, BP square equals to BC times BA. BP is the missing side, so we left as it is. So BP square equals to BC. BC is 1 times BA. BA is 6. So in conclusion, we should find out that BP square equals to 1 times 6, that is 6. BP square equals to 6. We took out of this equation and finally found out that the missing tangent BP equals to the square root of 6 units in itself. In the next step, I copied the right triangle APB in a new page, and we implemented the Pythagoras theorem, this right triangle APB. The hypotenuse AB is 6, and PB is square root of 6, and the only missing side is AP. We found out the missing side AP by implementing the Pythagoras theorem in this right triangle APB. So actually, this is the right triangle APB that I come from the original drawing. Again, the hypotenuse AB is 6 and PB is square root of 6. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the source of the perpendiculars. The hypotenuse in this right triangle APB is AB, therefore the square of the hypotenuse is AB square, and AB square must be equal to AP square plus PB square. AB is 6, therefore AB square is 6 square. This is 36, and this equals to AP square. AP is the missing side, so we leave it as it is, plus BP square. BP is square root of 6, therefore BP square, PB square is square root of 6 square, that is 6. So in total, we should find out that 36 equals to AP square plus 6. We subtract 6 from this equation, and we can find out that AP square equals to 36 from 6 is 30. So AP square equals to 30. We took out of this equation and finally found out that the missing side AP equals to the square root of 30 units in itself. this is the missing side AP. This is equals to 30 to the square root of 30 units in itself. AP is the diameter of the green semicircle. Therefore, the diameter over 2 is the radius. So AP over 2 is the radius of this green semicircle. Okay, again, the radius of the green semicircle equals to the diameter AP over 2. AP is equal to 30. Therefore, AP over 2 is equal to 30 over 2. So the radius of this green semicircle equals to the square root of 30 over 2. Again, the radius of this green semicircle R equals to the square root of 30 over 2. And in this question, we are looking for the area of this green semicircle. The area of this green semicircle equals to pi r square over 2. Repeat again. The area of this green semicircle equals to pi r square over 2. So it is pi, r is equal to 30 over 2, therefore r square is equal to 30 over 2 square divided by 2. Open the brackets here, we found out actually that the area of the green semicircle equals to pi, and square root of 30 square is 30, over 2 square is 4, divided by 2. So the area of the green semicircle equals to pi times 30 over 4 over 2. 30 over 4 over 2 is 30 times 30 over 4 times 2. So in total, this expression equals to 30 pi over 4 times 2. Here, 30 over 2 is 15. So in total, this expression equals to 15 pi over 4. Here, 15 over 4 is 3.75. Therefore, in total, this expression equals to 3.75 pi. Or in terms of numbers, 3.75 pi is 11.78. So in conclusion, in both methods, we found out that the area of this green semicircle equals to either 3.75 pi square units, or in terms of numbers, it is equals to 11.78 square units. Okay, thank you very much.